to networks. I hope everybody had a nice Eid. So to start with, I'll first revise a bit. Okay. Right, Ramanand, you can start this picture as well. Okay, Ramanand, am I clear?
Yes, sir, but
Audible?
in picture, yes, sir, it's clear.
I'll stop the picture then if it's taking
No, sir,
a lot
now
of
it's
time.
clear.
Right. Okay. Now we are discussing chapter regarding network layer. All right. If we go bottom up approach, network layer forms the third layer. The sheet that I have given you, the separate one in which we have examples and OSI model, says that the layer number 3 is the network layer, and we call the protocol data unit of network layer as packets. So if I talk about packets, I'm talking about network layer. If I talk about frames, I'm talking about data link layer. And if I talk about bits, I'm talking about the physical layer. The device or the components that basically forms the network layer is the router, as well as the other devices which you see having a part of the network layer are the two end nodes, the sender and the receiver. The main functions that we see in network layer are addressing, access to media. This is the logical addressing. We had physical addressing in the data link layer. The logical addressing here we mean the IP addresses. We have path determination, forwarding, as well as routing, as well as reporting the delivery errors. I'll send you the links for videos for the routing. I hope that has been taken care of. So this is what we have within the network layer. The routing protocols first, the OSPF, BGP, RIP, which you would have hopefully gone through it. The second part is IP protocol, addressing conventions, datagram format, packet handling convention. And the last part that we see here is ICMP protocol, that is error reporting, the ping that we see, which we will come across in a little while. So basically IP protocol is the main protocol of the network layer. If we see examples, there are plenty of examples which are given in OSI as well as TCP. In TCP IP protocol, IP, IPsec, ICMP, IGMP, OSPF all belong to the network layer. And there is ATP as well as IPX for AppleTalk and IPX network-based systems. Let's first discuss about IP addressing, right? And for that, we'll first discuss the IPv4 address. Now, every node that gets connected to the network has its own address. We know that. And also in a previous class, I think some class back, we discussed that we have a number of different, addressing that we come across. Like in data link layer, we have MAC address, network layer, IP address, as well as if we go to higher layers like application layer, we have host names. Also, we discussed about a point in which uh, there was a question that why do we need IP address if we have MAC address, or why do we need MAC address when we have IP address? This we took in our previous class as well. Now, since we know that to be connected to a specific network, we would need an IP address. IP address is not permanent. It keeps on changing. You move from one network to another network, your IP address changes. Like for example, you have, you are in the hostel, you check your IP address. We have done commands to check your IP address like IP config or IF config, and you'll get to know what your IP address is. Move from there, come to the department and connect to the department's network, you will see a different IP address. Or within a hostel, you're connected through LAN, check your IP address. Now you're connected through Wi-Fi, check your IP address. You will see that there is a difference between these addresses. You will not have the same address. You'll be connected differently. So the first component in the network layer protocol, we have IP addressing, and there are two types of addressing that are common. One is IPv4 address and another is IPv6 address. IPv4 addressing is an address typically for a single link into the network. Let me see. Okay. So if we have a link here, if we have a link here, each link has its own IP address. Okay. So typically a single link here would have a single IP address on this end and another IP address at the other end where it is connected. Boundary between the host and the physical link here is called as interface. This is an interface. This is an interface. Like this is an interface, this is an interface, this is interface, this is an interface. So this is the boundary between the host that's here and the physical link that is here that goes across. Okay. And every host and a router is capable of sending and receiving a datagram. In this case here, this is our host and this is our router. This is the link that is connecting them. So an IP address on this end, IP address on this another end. So this also means that each host and router interface should have an IP address, own IP address, a unique IP address. And what is an IP address? IP address is a 32-bit long IP address. That is number one. So if it's a 4-byte address, this means there are 2 to the power of 32 possible IP addresses. 2 to the power of 32 possible IP addresses. And how it is written? It is written in a dotted decimal notation. What I mean by dotted decimal notation? 192.168.1.1. This is what I mean by dotted decimal notation. And within this, you will see that each byte here, say here 192 that I have encircled, okay, is written in its decimal form, and each byte is separated by a dot or a period that is in between these. So each byte is separated from other byte by a dot or a period. 192 here is the decimal equivalent of first 8 bits of the address. Thus, it would be like we would be having a binary notation of something like this. Something like this. Okay, this is how actually an IP address would look like. Another thing that we see here is IP address consists of two parts. That is this part, and then we have here the second part here. And see something that we have common here. The first part that we have is common to all those nodes which are within the same network or within the same LAN. I will encircle them with pink. They are connected to this switch and they are connected through this router node. And all the nodes that are within it have the same first 3 bytes in this case. This constitutes what we call as the network part. And the rest, like we have 1 here, 2 here, 3 here, 4 here, this is known as the host part. So basically IP address would have two parts. One is the network part, another is the host part. IP address is technically associated with an interface, and the network part determines to what network is this host, whether it's a router or a desktop or a laptop, whether it is connected to what network it is connected to it. So in other words, the network part here that I have in this example, it would vary from example to example, from network to network, is 223.1.1.xxx. So this part, that is 223.1.1, determines the host part, the network part, and the remaining 3 decimals that we would have here, which I have denoted here by XXX, would denote the host part. All the nodes within this network share the common leftmost, how many? 8268, 24 bits. So 24 bits are shared by the nodes which are within the same LAN. This forms an IP network or simply a network. 24 bits they share is the network part. 8 bit that we have, I've mentioned here. This is 8 bit. This is the host part, and 24 bit is the network part. This 8 bit is also known as interface part of address. Is this part clear? Everybody got it? Okay. So network address here, in other words, is 222.1.1.0. I'll write it somewhere here. Just clear the annotations. So the network address that we have 223.1.1.0/24. And this oblique 24, what does it denote in this case? This denotes that how many bits of the IP address is of the network. All right. Just give me a minute. Oblique 24 says that the first 24 bits of the IP address is network part or belongs to the network. This is also known as network mask or net mask. This is the network part, which indicates the leftmost 24 bits of the 32-bit IP address is network address. Another word that we use is network prefix, network mask or network per, which again means that leftmost bits that define the network address or the IP address is network prefix. Any questions till now? If not, then I'll move towards the classes, the network classes. So this is what we discussed. The IP address, the subnet part, as well as the host part. Subnet part is that part, okay, which is of the interface. Another thing that you see, a router that connects this network also had that part, same network part. So you would need to have the same network part so that the whole of the network is connected to the router. Another thing that we see here, if a node, let me just mark it, if this node having an IP address 223.1.1 leaves from this network and joins another network, that is you moved from hostel to department, the IP address here would change from 223 to a new one, 223.1.3. Whatever is available, 27 is taken, 1 is taken, 2 is taken, so it can have something like 223.1.3. That's it, 3. This is depending upon the availability. That's why we say IP address would change once you move from one network to another network. You cannot send it, you cannot send a packet if you do not belong to that network, if you do not have the address belonging to that network. So we have here the next part that we call as IP address format. The first part that we see is CIDR, is classful addressing. After classful addressing, I would move to classless addressing. Let me just add here classful addressing. So what is basically this classful addressing? For this, I would need to draw a figure. I would have here, based on class full addressing, I would have 4 types of categories, which are the first one as class A, the second one as class B, the third one as class C, and the fourth one as class D. Now what are these 4 classes that we have for IP address? The class A says, right, the first 8 bits belong to the network. First 8 bits are the network part. The class B says that first 16 bits belong to the network part. The class C says that first 24 bits belong to the network part, and the class D is what we have as multicast addressing. I'll come to that as well. Which means here, this is also denoted like this would be 0, and then we have 1 0, so we have 0 here, then we have 1 0 and 1 1 0, as well as 1 1 0. This is how you would denote it, which in other words is that the first bit would be starting with this. A total of it here that we have across this one, this is 32 bit, okay. And to begin with, let's say class A would start from 1.0.0.0. This is the first address that we have, to 127.255.255.255. Since we are using the decimal notation, we would have the value at every byte from 0000 to FFFFFFF. That's the maximum possible. Or in other words, from 0000 to 11111, which would be in decimal equivalent starting from 0 to 255, 256 possible addresses that we can have. And this is for class A. We would have for class B starting from 128, since class A ends at 127, so add one more to it, 128.0.0.0 to 191.255.255.255. Then we have class C, which starts from 192 onwards, 192.0.0.0 to 223.255.255.255. And the last one that we have is class D, which starts from 224.0.0.0 to 239.255.255. We have some remaining addresses which can be taken in class E as well. Okay, but generally we say we have four classes. Thus, if we take first class, class A, how many we can have, how many networks we can have? It says the first 8 bits that we have is used for the network part. However, when the first 8 bits, the first 8 bits is fixed as 0, so we would have 2 to the power of 7 networks that would be available here in class A. 2 to the power of 7 networks. So in class A, we can have 2 to the power of 7 networks. And what is the remaining one? That is the 24 bits that we have. We can have hosts, or in other words, 2 to the power of 24. These many hosts can be accommodated within class A. This is what we have as class full addressing. And class D that we have here is known as multicast addresses. I'll just write here. These are reserved addresses. Any questions till now? No? Any questions? Okay, if you don't have any questions, I'll move to the next part. There is a problem with class full addressing that we just now studied. We studied this class full addressing. What is the problem here? Let us see. A question here comes that if a company wants two 2,000 addresses, okay, how many would class C provide? Yes, anybody? Can anybody answer this? If we use class C, what is class C? It is 24/24, means 24 bits are for network part, and the remaining 1 byte 2 to the power of 8 is for the host part. And how much is 2 to the power of 8? We have 256, out of which 2 are reserved. So we have only 254 which can be given with the help of class C. Now instead, what would you say? You would say, let's not give class C, give the company class B address. What is class B? B is 16, which says 16 bit is the network part, 16 bit is the host part. Fine. So how many are we supposed to get here? If we check this, we will get 2 to the power of 16, which comes to 65,500, let's say 34 possible addresses that we have for the hosts. Now, how many company wants it? The company wants 2,000 addresses. You are giving it class B addresses. You are wasting quite a lot of addresses here. $63,534 addresses are getting wasted. Okay. Because of this problem, in 1993, IETF standardized on a classless addressing known as CIDR, classless interdomain routing. Till now we are studying classful. Now we have classless interdomain routing, which says that the subnet portion of the address can be of any length. It's not necessary that you would have it as 8, 16, 32, and so on. Let it be X, where X denotes any number, not the fixed one. These networks came to be known as siderized network, CIDR, siderized network addresses. So network part of these IP address can be of any bit long rather than 8, 16, 24, denoted by here a.b.c.d hyphen /x, where x is network part, network prefix or network mask denoting the leading bits, and x can have any value. So in the previous example that we just now took, if we now move from this class full addressing to class less addressing, what would we have here? The same question, the company wants these many addresses. Class A gave this many, class B gave this many. Okay, now let's have class less addressing. Or CIDR. Now in this case, would we have A dot B dot C dot D oblique X? So how much should this X be here? That's the question. X should denote our leading bits. Organization needs 2000 IP addresses. How many would we allocate? In this case, X equal to 1 would provide us an IP addresses equal to 2048. So the first 21 bits specify organization's network address common for all PCs in the organization, and that 21 would be the host part, and remaining 11 bits would identify the host, and from remaining 11 bits we will get 2 to the power of 11 IP addresses, that is equal to 204. All right, to the these 2048 out of 2000, remaining only 48. You have saved a lot. So compare the networks which were siderized with classful. You can see the difference, how many IP address that you had saved. And then we have another concept that within this organization, the 11 bits that you have used, the rightmost 11 bits, can be further divided using what we know as subnetting. We'll come to that as well. The concept of subnetting, NAT, and so on income. Do you have any questions till now? I hope everybody understand. Do you want me to repeat? Is it clear? Is it clear? Ramanan, am I audible?
Yes, sir.
Is this clear?
Yes, sir.
Okay, fine. So this was CIDR. Next part is how do you get an IP address? There are two ways by which you can get your IP address as a host. The first one is manual configuration. The second one is known as DHCP. What is manual configuration? You go into the system, all right, go to the networks and you key in your IP address. Let me see what I can share here. Can I share? I don't see I have an option of sharing there, but I can just go to the settings, properties. Ramanan, can you see this?
Sir, there is gray screen, something like mesh. It's not visible.
Still the same?
Yes, sir. Ah, yes, sir. Now it's okay. Now it's.
Okay, you can see edit IP settings,
Ah,
right?
yes, sir.
Okay, so the first way is manual configuration. In manual configuration, what you would do is you go on and key in the IP address like I'm doing here 192.168.1. Let's say 5. Okay, I have to say how much is my subnet prefix. Let's say 255. I'm using class C address because it's 192. If you see the table that I previously mentioned, 192, starting from 192.0.0.0, it is supposed to be within class C. So I would have the first 24 bits within the class C as the network part, 255.255.255.0. So I'll put this as gateway is to what network I'll be connected. Let's say I have the gateway IP address as 1.1, DNS and so on, and I can save it and I would have this configuration. For this, I should know to what network I'm connecting, what is my gateway, what is my DNS and so on. The other method that we have is what we call as DHCP. It's written here, automatic DHCP. And what does automatic DHCP means? It is a protocol Ramanand, am I back on PPT?
Yes, sir.
Okay. The DHCP is a protocol known as Dynamic Host Configuration Protocol. You will get certain information regarding your PC so that you can get connected to the network directly. What information it would include? It would include the IP address, it would include the first hop router or what I just mentioned as the default gateway, the DNS, the primary DNS, the secondary DNS and so on. This all information would be sent by your router or by the DHCP server to which you are connected, and you will get the information and it would be programmed within your PC. Now what happens after every restart? It gets cleared, you will get a new one because it's a dynamic configuration protocol. It gets changed, it gets updated. DHCP is automatic, it's a plug and play protocol. Keep in mind, it would give you a temporary address. So once you move out of this network, your IP address would changed. From there, you'll get another one that will be given. So the goal here is to allow host to dynamically obtain its IP address from the network server when it joins the network. it can renew its lease on address in use, it allows reuse of addresses, and it's support for mobile users who wants to join network as well. How it works? The host broadcasts DHCP discover message. DHCP server listens to those messages, and once it receives that, it responds it responds with a DHCP offer, which is a reply back message here. And then Ramanand, you should keep track of attendance as well.
Yes, sir.
And then the host, thank you. Then the host requests IP address. Okay, after discovering that there is a DHCP server, which is a DHCP request message, and DHCP server sends back the DHCP acknowledgement message that yes, this is what your DHCP is supposed to be, and it will give it its IP address, its network prefix, what we just now had, the first hop router, which was the IP gateway, as well as the DNS, primary, secondary, and so on. All right, this is what we have about DHCP. This is a client which has just arrived, which has joined. It sent a message with broadcast across everybody here looking for DHCP server. Is there any? Once DHCP server received it, it replied back. Then the client sent another message saying that I want the IP address. This is how the DHCP client scenario works. This is arriving client. Arriving client sent a message saying, is there any DHCP server out there? Everybody received this broadcast packet. DHCP server within the network also received it, and it knew that it is for me. It replied back, I am the DHCP server. Here is an IP address that you can use. Back to the client. Client says, okay, I'll take that IP address. DHCP acknowledged back and says that, okay, you have got that IP address. It registers. Why DHCP registers this client with that IP address within its server? So that this address is not given to anybody else within that time. So that if another client joins in, it is given a different client. It keeps a registry of the addresses, that this is the IP address and this is the host. And it would give it for a certain interval of time. After that, the lease has to be renewed. Say I give you this for 1 hour. After 1 hour, it will check again. Are you still using it? Yes, I'm still using it. So lease would continue for 1 more hour. If he is no more there, if he has left it, the network, if he has switched it off, his PC, then this IP address would be available and somebody else can use it for that duration after this. Once this PC starts again, it would again have to ask for an IP address through the same procedure that is given here as client server scenario, and this time it can get a different IP address. It can get same, it can get different depending upon the availability of it. Okay, this is what we have basically, DHCP or dynamic host control protocol. Clear the annotations. And like I just now mentioned, DHCP is more than an IP address. It does not only give you the first IP address, it does not only give you an IP address. In addition to it, it will give you some other information of the network as well. Like all the packets from your IP address should be directed to which IP address so that it can go beyond your network. That is what we call as first hop router for the client. This first hop router you might have studied in the routing part. Also, it is the default gateway for that IP address. It will give for the name and IP address of DNS as well as the network mask. This is an example of DHCP. You can go through it. This is, if you open the packet using Wireshark, this is what you can see within it. Now again, if you would have used manual configuration, you would have kept the IP address physically, like I just now told you. You open the network properties and put in the IP address and then save it. Your system would start working fine. But the problem with the manual would be that, let's say another friend of you keeps the same address. Okay, IP address is supposed to be a unique identity within the network. Now, if two of them have the same IP address, your router, your gateway know where to send this packet, whether this is the correct IP address or that is the correct IP address. So you would have what we know as IP address conflict. Your operating system would give you a message that there is an IP conflict within your network. Before we go to IP addressing in NAT, there would be typical questions that would be asked, like there's an IP address. You have to tell what class of IP address it belongs to. We took here this classes, all right, classful addressing. We mentioned here that from 0 to 127, it is this 127 to 199, the first byte. Let me just write that down. And also there is the fifth one, which I forgot to mention here. Let me just draw a box here to indicate that beyond this also there is one, this one. This we call as class E. This one as class E. Now what is this class E? Class E has addresses which start from 11111 that I mentioned here. Just let me use points. Or in other words, another thing that I can mention here that will make things easier for you. Class full addressing, class A, the first byte, okay, is 0. This means the first byte would start from 0 to 127. So any address having the first one as 0 or anything between 0 and 127, this is class A. Then we have class B, 128 to 191. So check the starting address. If it belongs to something like this, it is class B. And the third one that we have here, class C, if it's from 192 to 223, class C. Fourth one that we have is class D, is 224 to 239, like and so on. Then we have multi-class addresses. And the class E, again the reserved one, is from 240 to the last one, 240 to 255. This is the network part of it. Another way by which you can determine what is basically class E, it was class D was multicast addresses, and class E was denoted for future use, that we'll use for future. But then IPv6 came, which we'll study next. So starting with the first bit, okay, check Is first bit 0? Let me just write here. Now how to determine what address we have? I'll make a small flow chart to make you understand that to find whether this IP address belongs to which class. So if first bit is 0, this means it is class A. If not, move on. Check if first bit is 1. If first bit is 1, it can be what? If first bit is 1, then what? Check second bit. Within second bit, if second bit is 1, is 0, it is class B. Or if second bit is 1, check third bit. In third bit, if third bit is 0, it is class C. Or if third bit is 1, check fourth bit. So from here we can see the last part, if fourth bit is 0, it means it's class D. If fourth bit is 1, it is class E. I hope you understand this part. By seeing your first bit, you can decide whether it's A or B or C or whatever. If it's not 0, then move on to the second bit. And likewise, you can find. So if it's first bit as 0, class A, second bit as 0, class B, third bit as 0, class C, fourth bit as 0, class E. And if all are 1, 1, 1, 1, the first 4 bits are 1, 1, 1, 1, it means it is class E. Now, if I give you a question like, find the class of an IP address. Okay, I have an IP address 134.12.16.55. What would you do here? You would check the first byte of 134, right? The first byte is 134. And 134 lies between the addresses which is 128 and 191. Here 128, 191, 134 lies. So obviously it belongs to class what? B. I'll ask you a question. I have an IP address 227.16.54.255. Let's say 250. What class is it? The first byte is 227. 227 lies between 224 and 239. This obviously means that IP address belongs to class D. So keeping this in mind, the host part, the host ID and the net ID, you can actually decide to what IP address does the, to what class does this IP address belong. it is clear? Any questions? Okay, the next part is now you have to send the datagram from A to B. We have A here, we have B here, we have C here, there's the router, and let's say we have D here, that is the destination. So this part would take care of addressing, routing, as well as forwarding. Now once the A host has to send some data to B or D, it will receive a packet from the higher layer, let's say this one, at the network layer. And within this packet, it would add two things. One is the source IP address and the destination IP address. This would be kept within the header of the packets network layer. Then it passes this to the data link layer to the physical layer, then it sends it across. There are two scenarios that come into being here. One is A sending to B, this one. Another scenario, A sending to D. Let's take the first scenario, A sending to B. Now this packet is to be sent to B, which is having IP address 223.1.1.4. Try to understand here. It will take care of the data link layer also, how it would be sent. So two things that would be added here within this packet would be the source IP address as well as the destination IP address. These two things have been now added within the packet. What is the destination IP address in this case? The destination IP in this case is okay. The destination IP address in this case is 223.1.1.4. And what is the source IP address? 223.1.1, which in both the cases mentions that I am sending from this IP address to this IP address, and this IP address belongs to the same network. After this, the packet is passed on to the data link layer. The data link layer takes this whole as the datagram from the network layer and adds the source address, that is the source MAC address, and the destination MAC address, that is the physical address. How does it get the destination MAC address? It uses its ARP. With ARP, it then puts in the MAC physical addresses, and then what does it do? It broadcasts the packet. So once it broadcasts the packet, it goes to C, it goes to this, as well as it goes to the third one, that is the B. Now C here is the router, its interface takes this packet, it checks that the destination MAC address is not the one which is supposed to be, so it discards it. This one also checks it, discards it. But B takes it, compares its own MAC address with the destination MAC address of the packet, it accepts it, takes it to the network layer, checks the source address, checks the destination address. Within the destination address, it sees that yes, it matches the destination IP with its own IP. At this level also, it is correct. It accepts the packet. This is a second transmission. This is how it happens within the network. The second part of it is, if the host here, that is A, has to send to the destination, which is D, which is beyond its own network. Why is it beyond? Because it doesn't belong to it. It's not having the same IP address here. We can see this by our host ID. This is the network prefix of it, and this is the network prefix of it. Obviously, the third byte is 3 here and the third byte here is 1. This denotes that it's a different IP address, a different network. And if I ask a question here, that to what network does this belong to? Check the first one, that is 223, right? 223 belongs to what class? From 192 to 223, it is class C. So both of these are belonging to class C networks. Okay. Now since A has to send to D, what would they do? The network layer again receives this from the transport layer, adds its own header here, and within this header there would be some information. What information? The source IP address, the source IP address, as well as the destination IP address. Then passes on this packet to the data link layer. What does data link layer do? Data link layer puts the source MAC address and the destination MAC address. But keep in mind here, the destination MAC address, the ERP does not have the MAC address of D here, because D is beyond its network. ERP would have the addresses within its LAN only, within its network only. So it would put the destination MAC address as the MAC address of this interface of the router. Then it broadcasts the packet. So this PC received it, this PC received it, as well as the router received it. This PC, first one, compared it with the MAC address of the packet with its MAC address. It says no, it is not for me. It discards it. The same for this one. The router here takes this packet, okay, and then checks the destination MAC address. The destination MAC address is its MAC address, so it accepts it. Then checks the destination IP address that is given in the packet here. It sees that the destination IP address is this one, right? Now router, by its properties of having a routing table, it would have defined a path for this packet to route from A to D. It would check that the best way for this packet to receive to D, let's say, is this path. So it would forward the packet from this link, that is the incoming link, to this link, that is the outgoing link. So this is the incoming interface of this. This is the outgoing interface. Router here do routing as well as forwarding of the packet. Routing would be end to end from A to D, and forwarding would be from incoming link to the outgoing link. And thus within here, it will move on to the router here. The router here again, with the help of the data link layer, would broadcast the packet. It would reach to D. D would check the MAC addresses. If it's correct, then it would move to the next layer, that is the network layer, and within the network layer the IP addresses would be compared. If it's accepted, then it would go to the higher layers. This is how a datagram is sent from the source to the destination using the network layer. Any question? No? Okay, if you have any questions, just ask, otherwise I'll end the class. Next part would be the IPv6 addressing. or we have to first take IPv4 datagram format, which we'll take in the next class. Any questions? All right, Ramanand, I believe there are no questions, then we can just end this class. In the
Yes.
next class, we'll take IPv4 as well as IPv6 datagram format.
Okay.
All right. Take care and stay safe. Bye-bye. Properly can revise it through the YouTube link as well. The links would be shared by Ramanand as well as the links would be on our, departmental website. Bye bye.